Good. So, happy birthday, Ernie. We're going to talk about excess and limiting reagents and percent yield. Get ready, get set, go. So quick review, remind me, what are the 5 main types of chemical reactions that we talk about? When we classify reactions, what have we got?
Decomposition,
acid base,
the double replacement, single replacement, and
synthesis.
Yeah.
Oh, sorry, you already said that. Whoopsies.
I'm trying to think. Redox.
Acid base.
Yeah.
Right?
Mm-hmm.
So acid-base neutralization is a special kind of double replacement. There's one more of our 5 main.
Oh, combustion.
Combustion, perfect. So combustion is our other. And then double replacement, we can have acid-base neutralization as one special kind of double replacement. And then we also have precipitation reactions. Precipitation reactions as another kind of double replacement reaction in which we start with 2 solutions, and then one of the products is actually a solid, which forms clumpy stuff that sink to the bottom of your test tube, which is why we call it precipitation, because things like fall from the sky, fall through the test tube. Good. So let's review really fast, writing some balanced chemical equations. So I've got hydrogen gas and oxygen gas combined to form water. How would I write that as a balanced chemical equation?
(2H2 plus O2 equals H2, 2H2O).
Perfect. Brilliant. Remember that hydrogen gas and oxygen gas are both diatomic. They come in 2s when they're elemental. Forming water, to balance the equation, we need to have 2 hydrogen gases, 2 waters. Perfect. How about, oh, tell me before we move on, what kind of reaction is this?
Synthesis?
It is synthesis. Perfect. Good. Next one. Calcium carbonate produces carbon dioxide and calcium oxide. What's that going to look like in an equation?
CaCO3.
Perfect.
CO2 plus CaO.
Perfect. Calcium's a +2, oxygen's a -2, so that balances right out. Perfect. Is it balanced?
Yeah.
Good. What kind of reaction would this be? Decomposition. Perfect. All right. Hydrochloric acid reacts with zinc. What's this going to look like?
HCl plus Zn. Gives us zinc chloride and hydrogen gas.
I've got some things going wrong. What do I need to fix?
H2.
And?
Zn chloride is not balanced.
Good. So zinc is a +2 and chlorine's a -1. So we need a 2 here as well. So now let's balance our equation.
You put a 2 in front of the HCl.
Perfect. And what kind of reaction is this?
Single replacement.
Single replacement. Perfect. One more. Lithium hydroxide reacts with hydrofluoric acid. What's that going to look like?
LiOH plus HF. Is it going to give us lithium fluoride and water?
Yes, it is. Very nice. So what kind of reaction is this?
Acid-base neutralization.
Sure is, which means it's also double replacement. And we can look at those pieces moving around. We used to have lithium on the hydroxide. Now I have lithium on the fluorine, And this OH and this H, hydrogen that used to be on the fluorine, is now on that hydroxide. And HOH is the same thing as H2O. HOH is H2O. Perfect. So double replacement, acid-base neutralization. Great. So now we're going to switch over to this idea of excess and limiting reagents. So reagent is just another word for reactant. So we're talking really just about the stuff in the beginning. So let's say that I was making sandwiches and my recipe for a sandwich is 2 pieces of bread and 1 piece of cheese. 2 pieces of bread, 1 piece of cheese. This makes a sandwich. If I have 4 pieces of bread, how many sandwiches can I make?
2.
Yeah, so 2 pieces of bread, 2 pieces of bread. What if I have 4 slices of bread and 1 slice of cheese? How many complete sandwiches can I actually make?
1.
Well, 1, exactly. Because I'm going to run out of cheese first. I'm going to use 2 pieces of bread and that piece of cheese to make 1 sandwich. I'm going to have 2 extra pieces of bread. Because I run out of cheese first, I would call cheese my limiting reagent or reactant. Because I have leftover bread, I'm going to call that my excess reagent, my excess reactant. So let's apply it to chemistry instead of sandwiches. So I've got this lovely, already balanced equation. So very kindly in a 1-to-1 ratio, but we really only care about the reactant, so it's a 1-to-1 ratio. If I have 1 mole of sodium hydroxide and 1 mole of nitric acid, sorry, that's a 2. If I have 1 mole of sodium hydroxide and 2 moles of nitric acid, which one am I going to run out of first? They're in a 1-to-1 ratio. What am I going to run out of first?
Sodium hydroxide.
For sure. I'm going to run out of this first. So this will be my limiting reagent. This will be my excess. After that 1 mole of sodium hydroxide reacts with the nitric acid, how much nitric acid in moles will we have left over? How much excess will there be?
1.
Exactly. So since they're in a 1-to-1 ratio, if I use 1, I need to use 1, which means I'm going to have 1 left over. So sodium hydroxide would be my limiting reagent, and I'm going to have 1 mole of nitric acid in excess. Let's do the same thing with this, this combination of quantities. What if I have 2 moles of sodium hydroxide and 1 mole of nitric acid? What will be my limiting in this example?
Nitric.
Exactly, the nitric acid is now going to be my limiting reagent because in a 1-to-1 ratio, if I have 1, I need 1. How many moles of sodium hydroxide extra would we have?
One again.
I would have 1 mole in excess. Perfect, perfect, perfect. What if I have 5 moles of sodium hydroxide and 5 moles of nitric acid? What is the limiting reagent?
There isn't one.
There is not one. They're perfectly balanced. Good, easy peasy so far. So when things get tricky, like this, we have to think maybe a little bit harder. So here I've got 5 moles of iron 3 oxide, and I've got 6 moles of carbon monoxide, and they react. What is limiting? 5 is less than 6. Does that mean my iron 3 oxide is limiting? Because 5 is less than 6?
Not always.
Not always. And in this instance, I have a 1-to-3 ratio. So if I have 5 moles of iron 3 nitrate, and it's in a 1-to-3 ratio with carbon monoxide, how many moles of carbon monoxide would I need if I had I would need 15 moles. Do I have 15 moles?
No.
I only have 6. So what's my limiting reagent? That carbon monoxide. So even though there's a greater number of moles of carbon monoxide, because my ratio is a 1 to 3, I need 3 times as much carbon monoxide as I have that iron 3 oxide. And so if I have only 6 moles, that's not enough to react with all 5 moles of that iron oxide. So my limiting reagent is going to be that carbon monoxide. So now I want to know how much excess reactant will we have. Carbon monoxide is the limiting. Iron 3 oxide is my excess. How many moles will I have left over?
3.
Tell me why. You're exactly
Because for every 1 mole of iron oxide that we burn, or well, that reacts with carbon monoxide, 3 moles of CO are used. So that's 2 to 6 is 1 to 3. So it'll all go away after 2 moles have been used.
perfect. So because that iron 3 oxide to carbon monoxide ratio is 1 to 3, if I use 6 moles of carbon monoxide, that means I'm using 2 moles of iron 3 oxide. 1 to 3, 2 to 6. I have 5 moles. I use 2. That means we're going to have 3 moles of iron 3 oxide left over. So far, so good?
Yep.
All right. So let's do this one. So phosphorus 5 oxide reacts vigorously with water according to that equation. If we combine this many grams of phosphorus 5 oxide with this many grams of water, what's our limiting reagent going to be? How can I figure this out? What do we need to do first in stoichiometry all the time?
Mole conversion.
Got to get to moles. Exactly. So I need to convert my 5 grams of phosphorus 5 oxide to moles, and we have to also convert our 1.5 grams of water to moles. What's kind of nice about this question, they gave us the molar mass of water and that phosphorus 5 oxide to 83.88 grams per mole and 18.02 grams per mole. So we could go ahead and convert these to moles and then look at our 1 to 6 ratio to figure out our limiting reactant. I'm going to give us another option. Another possible way to solve this, we could look at this next part of the question where it's asking us to figure out how much phosphoric acid is going to be produced. So instead of just going to moles here, I'm going to go ahead and switch all the way to moles of this phosphoric acid. So in this one, I've turned my grams into moles of that phosphorus 5 oxide. I'm going to use the balanced equation to get rid of phosphorus 5 oxide and turn it into phosphoric acid. And do the same thing for my water. So my water is a 6. Phosphoric acid is 4. So then we can see that our grams cancels out, our P4O10 cancels out, and we have moles of phosphoric acid, that product, left. Same thing here for water. I canceled out my grams of water. I had moles of water. I canceled out water. Now I have moles of phosphoric acid. Both of these calculations are going to give me moles of phosphoric acid. Luckily, I have my calculator right here. 5 times 1 times 4 divided by 283.88 divided by 1 gives me 0.0705 with sig figs moles of phosphoric acid. Same thing for my water, 1.50 divided by 18.02 times 4 divided by 6 is going to give me 0.0555 moles of phosphoric acid. Tell me, friends, what's my limiting reactant?
The water.
Good, because I can make less phosphoric acid with that water, the water is going to be limiting. So water is that limiting reactant or limiting reagent. So this next part of the question, it's going to make sense why I chose to turn everything into moles of phosphoric acid. This next question asks me, how much phosphoric acid could we make? Should I pick the excess or the limiting?
Limiting.
For sure, always the limiting. So I'm going to take this guy, 0.0555 moles of phosphoric acid, turn it into grams. They didn't give us the mass for that, so we're going to have to actually figure it out ourselves. So hydrogen is 1.01 times 3. Phosphorus was, I had it written down, 30.97, and then oxygen is 4 times 16 for a total of 98 grams per mole. So 98 grams per 1 mole. 0.0555 times 98 gives us a grand mass of 0.054 with sig figs 4 grams of phosphoric acid. Good? Yes,
Yep.
yes, good. All right. Are we ready to flip a screen or need a second to think about this?
I'm good now.
Good? Anybody need more time? All right. Next, similar example. So here we have 7.40 times 10 to the minus 2 grams of magnesium and 15 cubic centimeters of 2 moles per cubic decimeter hydrochloric acid. Hydrogen gas produced was collected in a gas syringe. State the equation. We're going to start with state the equation. What are we going to do?
CO.
Magnesium chloride plus hydrogen.
What did I do wrong?
Unbalanced. I mean, the charges.
Cl2 on the end and
Yeah,
H2.
my charges are not balanced. So what do I need to fix?
You need to add a chlorine and a hydrogen to the reagent. Or sorry, the products.
Perfect, perfect. Because magnesium's a +2 and chlorine's a -1, I need 2 of those chlorines to balance out that magnesium. Hydrogen is diatomic, it's always going to be 2 when it is elemental. So now I need to balance my equation. I'm going to put a 2 in front of that HCl. Perfect, I've got my balanced equation. Determine the limiting reactant. So because they're talking to me about hydrogen gas, I'm going to assume that we're going to use that eventually. So I'm going to use hydrogen gas to compare my 2 reactants. So I'm going to start with that magnesium, 7.40 times 10 to the minus 2 grams of magnesium ribbon. And let's see. Mass of magnesium ribbon is 24.31 grams per mole. And then I'm going to go all the way to hydrogen gas. I'm going to compare moles of hydrogen gas. So 1 magnesium to 1 hydrogen gas, that's kind of nice. Good. So then my calculator, 7.4 times 10 to the minus 2 times 1 times 1 divided by 24.31 and also divided by 1.00304 moles of hydrogen gas, because we canceled out grams and then we canceled out magnesium. Let's do the same thing for our hydrochloric acid, but its concentration, which is kind of weird. So I've got 15 cubic centimeters of this 2 moles per cubic decimeter concentration hydrochloric acid. How am I going to figure out moles from that information?
You divide them by 1,000?
Yep, step 1, I need to turn my cubic centimeters into cubic decimeters. Perfect. So now I have cubic decimeters. What can I do with this to get to moles? Oh, I should put my HCl in there. If I have decimeters cubed and I have decimeters not to the positive 3 but to the minus 3, what can I do? Or what even does that minus 3 mean? What does that minus 3 mean?
It's 1 over dm to the third.
Exactly. So instead of writing 2 moles times cubic decimeters minus negative cubic decimeters, I can write 2 moles over 1 cubic decimeter. What does that do to my cubic decimeters here and here?
It cancels them.
It does. So now I have moles of hydrogen chloride, hydrochloric acid. Because my question is talking about hydrogen gas, I'm going to go ahead and convert my hydrochloric acid to hydrogen gas. I have 2 HCl's. I'm going to put it here so that my HCl's on top and bottom cancel out. And then I'm going to put my hydrogen gas, one of them, up here. So now we can do that calculation. 15 divided by 1,000 times 2 times 1 divided by 2, and that's going to give us 0.015 moles of hydrogen gas. So what's our limiting reagent?
Magnesium.
Yeah, because this is quite a bit smaller than this. Magnesium is going to be our limiting reagent. So hold on to this number, 0.00304. Here's my next question. What would be the theoretical yield of hydrogen gas? Theoretical yield is how much ought you make. This is how much we ought to make. So we already have the answer to that question. Theoretical yield, how much should you make? Stoichiometry says we ought to make this much. So our theoretical yield in moles is 0.00304 moles of hydrogen gas. How many cubic centers would that be? What am I going to have to do now? What formula that we learned last class should I use?
PV equals nRT.
For sure, we're going to use PV equals nRT. Pressure is given to us here, 1.01 times 10 to the 5 pascals. Volume is what we're trying to find, so I'm going to leave that be. N is moles. That's totally what we just figured out. R is our ideal gas constant, which is given to us in our data booklet, 8.31 joules, moles to the -1, Kelvin to the -1. And then temperature is 20 degrees Celsius.
But it needs to be in Kelvin, right?
Needs to be in Kelvin, exactly. I'm going to make that mistake on purpose every single time just so that you guys are always thinking about the fact that that's a mistake to not make. How do I turn my 20 Celsius into Kelvin?
Plus 283.
273. Super
Okay.
good. 273. Good. So 20 plus 273 gives us 293 Kelvin. So now we're going to divide both sides by that 1.01 times 10 to the 5 pascals, which is going to give us volume. So 0.00304 times 8.31 times 293 divided by 1.01 times 10 to the 5th power gives me a volume of 7.3, how many sig figs do I have? 3. 7.33 times 10 to the -5. What is my unit label?
Cubic centimeter?
Do I have cubic centimeters yet?
Oh, no.
Not quite. So remember that pressure is in pascals and volume is in, anyone remember what volume gives us? It's a
Is it
weird
cubic
one.
meters?
It is cubic meters, exactly. So right now I have cubic meters. And so of course IB wants us to do some conversions to get to cubic centimeters. How many centimeters in a meter? How many centimeters in a meter?
100.
100. So I have 100 centimeters in 1 meter. But can you guys see that through the colors? Kind of, sort of,
Yeah.
ish. Good. So I have 100 centimeters per meter, but I have meters cubed. So I have to do that 3 times to cancel out 1, 2, 3, 1, 2, 3, which is going to give us then centimeters times centimeters times centimeters, centimeters cubed. And so 7.33 times 10 to the -5 times 1, 2, 3, 4, 5, 6 zeros, 10 to the 6. Looks like we've got 73.3 cubic centimeters of hydrogen gas. Good?
I think so.
Right? What's magical about these questions on IB is that there's partial credit. So set things up, get as much done as you can, gather those points. A little bit goes a long way. Partial credit is your friend. All right, let's do one more and then we'll talk about the lab and we will call it a day. And we will call Monday a work day. So here we've got some grams of iron added to a solution of copper sulfate. Figure out the limiting reactant. I'm going to skip ahead a little bit and I see I'm looking for mass of copper. So I'm going to do something with copper in my limiting reactant math. So tell me where to start. What should we do first? Or actually, let me ask this. Do you want me to be quiet for a little bit and you work it out and then we go over it after you've had a chance to try it yourself? Is that better?
Sure.
Okay. I'm going to put how many minutes? 4?
4.
4 minutes on the timer. We'll be back in 4. I'm going to pause the video because it'd be really boring to have a recording of 4 minutes. I'm going to pause recording. When we start talking again, someone remind me to unpause the recording so that I don't forget the end. Good? All right, that was our, 4 minutes. I'm going to resume. Oh no. So I paused screen share. I didn't pause record. That was super not helpful. I'm so sorry. Good. So here we were. It'll be a super boring 4 minutes in the middle of that video. So we were here. Tell me what you get. What's our limiting, what was the limiting reagent?
I got iron as the limiting reagent.
Got iron. Anybody agree, disagree? All right, well, let's work it out and see, see what it looks like. So 3.26 grams of iron. What's our molar mass of iron according to the handy dandy periodic table? 5.85 grams per mole. And then again, because I see this copper down here, I'm going to go ahead and convert to copper right away. So I have 1 iron I'm going to put here. I have 1 copper I'm going to put here. So 3.26 divided by 55.85, 0.0584 with sig figs moles of copper produced. Let's do the same thing with our 80 cubic decimeters of 0.2 blah, blah, blah. So I have 80 centimeters cubed. Turn those centimeters cubed into decimeters cubed, 1,000 cubic centimeters in 1 decimeter. Turn my decimeters into moles. I know that I have 0.200 moles per cubic decimeter. And this is all, I should have written this in here. This is all the copper sulfate. And I want to get rid of copper sulfate. I'm going to turn it into copper. It is also a 1-to-1 ratio. 1 copper to 1 copper to sulfate. So then what cancels out cubic, cubic centimeters cancels out, cubic decimeters cancels out, copper sulfate cancels out. And if I do 80 divided by 1,000 times 0.2 times 1, I get 0.0160 moles of copper. So what's our limiting reagent?
Copper.
The copper sulfate. Yep, this copper sulfate is going to be our limiting reagent.
I forgot to type an extra 0 on my calculator looking at it. I divided by 100, not 1,000. Oops.
Friend, all the time. I have to retype things all the time. I will usually do my math twice just to make sure I didn't miss a button on the calculator. Good. So now the mass of copper obtained experimentally was this percent yield. What's our formula for percent yield?
Actual over experimental times 100.
Actual over theoretical. So actual is the experimental.
Oh, yeah.
Over theoretical times 100. Exactly. So what we actually made, and when we actually did the lab, right there, we actually made in the experiment that number of grams. Theoretical yield, how much should I make according to my math? So to figure out the theoretical yield, I'm going to take from my limiting reagent that moles of copper, turn my moles of copper into grams of copper. Copper is 63.55 grams per mole, 0.016 times 63.55. we should make about 1.02 with my sig figs, 1.02 grams. So what we ought to make, so 1.02 grams is our theoretical yield. Multiply by 100, 0.872 divided by 1.02. It gives us 85 point, with rounding and sig figs, 85.5%. We made 85.5% of what we should have made. How are we feeling? Are we glad we powered through today, or we should have made today a work day?
I'm glad we powered through, but I'm a little confused on one thing.
Yes.
So we're using iron to calculate the moles of copper, and then we use, I don't understand why we're doing that, because are we looking at how much copper is produced from the iron during the reaction?
Correct. So
okay.
Yes, in the math here, the math that I did here, I figured out if all of the iron reacted, what is the maximum amount of copper we could make? If all of that copper sulfate reacted, what's the maximum moles of copper we could make? And then when you compare those two, you're like, oh, the minimum is actually the maximum, because I'm going to run out of that copper sulfate first. The reason that I chose to focus on copper is because I saw copper down here. I knew that I was going to have to figure out those moles of copper eventually. So I went ahead and used copper to find my limiting reactant. Better?
Yeah, okay, that makes sense.
Good questions. Answers. All right. So classic chemistry, you can't get through your chemistry without mixing some baking soda and vinegar. So those of you who are at home, who have lab baggies, you have some extra aluminum weigh boats. What you are going to do in that aluminum weigh boat is figure out with stoichiometry how many grams of baking soda should you mix with how many milliliters of vinegar. If you do your math correctly, and if you pour your vinegar fairly slowly, those aluminum weigh boats that you have in your baggie will be just the right size for all your bubbles. If your math is off or you get a little splashy with your vinegar, you might have a little bit of an overflow. So do this by a sink, just in case. But what you want to do is math to figure out what mass of baking soda you should add to what volume of vinegar, so that you can make 0.50 grams of sodium acetate. So you're going to mix. You're going to have in your weigh boat a solution of sodium acetate and water. Water is also produced in this reaction. You're going to let it sit for a day or two in a warm spot to get that water to evaporate. And eventually, after a day or two, you should have a weigh boat with just sodium acetate, which is the ionic product of that chemical reaction between baking soda and vinegar. And then you're going to mass how much sodium acetate you actually made and calculate percent yield. Your experimental that you actually made divided by theoretical, which is that 0.50 that I am proposing to us. Good?
Sounds good. Can we heat that little weigh boat to make it go faster, or should it evaporate?
You can totally heat it up. Since it's an aluminum weigh boat, if you have your aluminum weigh boat at home, don't put it in the microwave, obviously, it's metal. But a nice sunny window, or if you have a fireplace, you have a fire going, you can like put it close to the, not like in the fire. You don't want it to boil, because then it'll splatter and make a mess. I am going to have open lab tomorrow. No, not tomorrow. Saturday. Tomorrow is Friday. Saturday, I'll have open lab. So if you want to come here and do it here, you definitely can. And we have the hot plates. So you could put your aluminum weigh boats on the hot plates for a little bit to warm them up, speed up that evaporation process. But if you've got a heater, a warm spot in your house, that'll speed it up nicely. Those of you who are home and cannot come to open lab, what I'm going to have you guys do is the math. Send me your math, and I will mix for you the quantities that you have calculated, and we'll go from there. Good?
Can I also like come to the open lab to discuss more about EE stuff?
For sure. For sure. No, open lab is like whatever you need to do, we can do. Some people come to open lab and they don't ever do any lab things. They just sit and work because sometimes it's easier to get work done when you're sitting at school than if you're home and cozy in your PJs and your slippers and stuff. So yeah, we can do whatever you need to do. Good?
Sounds good.
All right. Did I publish the lab on Canvas? Do you have it already or not yet? Sometimes I forget.
I think it's all on that like agenda thing on the Unit 5.
The list of things to do? Perfect. Then I remembered to click the publish button. Perfect. Yes, it is. Good. All right, my friends, that's all I've got. If you have questions, I will linger. If you have no questions, go forth. Have a lovely rest of your Thursday. Have a brilliant Friday. Have a good weekend. I will not see you on Monday unless you have questions. I will open Zoom optionally at noon.
Have a wonderful day, Miss Lentz.
Thank you. Bye, Cassandra.
Have a good day, Miss Lentz.
Thank you.
Bye,
Bye.
Miss Lentz. Thank you.
Bye. Bye. You guys are leaving too fast. I can't say goodbye fast enough. Bye. Oh, and I'm still recording. Oh my gosh.